in any form, right? So it can have poles and zeros. Okay, T of S can have zeros as well as poles. But the first case we took is 1 by Q of S. Okay, that means you don't have zeros. That is, zeros are present at infinity. Okay, there are zeros only at infinity, and you have only poles. That is, this function is called all pole transfer function. Okay, this function we took, and we have synthesized input. Okay, by selecting capital Q of S and obtaining constant k. Okay, so we have obtained constant k by applying limit s tends to 0. Okay, and we have determined k value. Okay, right. So in this module, and if you see in the previous class, so it was low pass filter. I told you this function was low pass filter. Okay, if the transfer function is in this form, so low pass filter, you have capacitors in parallel. Okay, you have seen in the last class capacitors are in parallel. Okay, so now let us see some other transfer functions. Okay, so we have seen this form in the last class. T of S is 1 by Q of S. Okay, this form. Let us see some other two-port functions, transfer functions. So how to derive, how to synthesize network for other two-port functions. Okay, we will see. So next thing is, suppose in the next transfer function, if you have zeros, okay, zeros at origin. Okay, so if all the transmission zeros are at origin, right? So instead of infinity, you have zeros at origin, right? So the synthesis proceeds by developing Z11 in KF2. Okay. So in the last class, low pass filter 1 by Q of S, we have converted driving point function into KF form 1. Okay. Remember that low pass filter KF form 1. Now if you have transfer function in this form, that is, you have all zeros at origin. Okay, you have all zeros at origin. That is, there are two zeros here, and these two zeros are at the origin instead of infinity. Okay, so if the transfer function is this form, like 1 by Q of S, so 1, so numerator is 1, then when numerator is 1, we say that there are zeros at infinity. Okay, so if the transfer function is this, okay, the numerator is s square. So if the numerator is s square, then we say that there are zeros at origin. Okay, this transfer function has zeros at origin. Okay, so poles you can see s equal to -2. So first we will confirm whether it is RC ladder network or not. So poles, if you have seen negative, it lies on negative real axis, so it is RC ladder network. Okay, so if you have this kind of function, that is s square, if all the transmission zeros are at origin instead of infinity, the synthesis proceeds by developing Z11 in KR2 form. Okay, KR2, not KR1, KR2 form, right? So, our Q of S will be same, right? So how to select Q of S also I told. So it should be interlacing. Okay, you should select Q of S, zeros of Q of S, interlacing the poles of T of S. Okay, so that's why we have selected S plus 1 and S plus 3, right? So then your driving point impedance function will become small Q of S upon capital Q of S. Okay, so this one you will get it right. So this thing, after that, so this is in S square form. Okay, all transmission zeros are at origin, so we have to convert into KF2 form. Okay, so the transfer function is same like the previous case, 1 by Q of S, but here it is in S square form. Okay, so we have to convert into KF2 form, right? So the same transfer function, convert into KF2 form, you will get this. Okay, so KF2 form, if you see how is the KF2 form, KF form 2, it is like this. You have S in the denominator. Okay, you have S in the denominator, right? You have S in the denominator. If you can see here, the S is present in the denominator. Okay, so you have to convert this by continuous divisions. Okay, in this way, so that such that the S is in the denominator. So you will get this constants. Okay, so then how to realize the network? Just this constant has to be substituted. So first thing is constant. So starting with resistor. Okay, so you have 3.3.3. Okay, and 0.19, 1.83, Okay, 0.19, 1.83, and 0.04 and 6.54. Okay. So this is a high pass filter. Okay, so you have resistors here in this fashion, right? So then it is a high pass network or high pass filter. Okay, so previously 1 by q of s, it was low pass, kf form 1, and this you have s square. So you are taking your driving point function will be same, but you will convert into kf form 2. Okay, then you will get high pass filter. And how to obtain the constants here? So same thing. So you have high pass filter, then you can make use of the condition s tends to infinity. Okay, s tends to infinity. Okay, so if your transfer function is t of s, k s square s plus 2 into s plus 5, okay, which is a transfer function, then k is obtained by making s tends to infinity. Okay, if you make s tends to infinity, 1 by s tends to 0. Okay, then capacity reactance, which is xc is 1 by sc, will become 0. Okay, so this reactance will become 0 in the sense the capacitors are short circuited. So there is a full transmission. Okay, so there is a full transmission. So you can obtain k value in this way. First, as s tends to infinity, okay, it is a high pass filter. S tends to infinity. You can find out what is the transfer function value with the from the given transfer function. Okay, s tends to infinity, 1 by s tends to 0. Okay, so here 1 by s tends to 0, you just apply here, so you will get k. Okay, remaining all in this s tends to infinity. If you do, you will only get k. Okay, so this is from the transfer function. And by comparison from the network, s tends to infinity, 1 by s tends to 0, so capacitor will become short. Capacitor will become short. There is a full transmission, you can see. Okay, there is a full transmission. So transfer function is 1. Okay, v2 upon v1 is 1, so you will get k is 1. Okay. So that is the, so this completes your synthesis of transfer function in this form. Okay, s square. So here the point to be noted is if all the transmission zeros means for this transfer function, two zeros are possible. Okay, because in the denominator the power is s square. Okay, so numerator also it should be maximum s square. Okay, for a transfer function. So two zeros are possible here, and if all those zeros are at origin instead of infinity, the synthesis proceeds by developing KF2 form. Okay, KF2 form. So you have to go right. You have to use KF2 form. Okay, but if you see the driving point function is same. If you see the driving point function is same. Okay, in the last class, 1 by q of s, and this class which is s square upon q of s. So the driving point function is same, but if it is low pass, if it is 1, if the numerator is 1, we are expanding by k form 1. That is zeros at infinity. Okay, so that is low pass network. But today we have seen k form 2. That is driving point function is same, but zeros are at origin. Zeros are at origin. It is a high pass network, which is this network. Okay, so that you have to take care, right? Seeing the transfer function, you have to apply the method, which, right? So these two forms we have seen. Now let us go to the next thing. Okay, next form, and this see this is the, you can remember in this way that high pass filter you have resistors in parallel. Okay, and low pass filter, if you see in the previous class, capacitors will be in parallel. Low pass filter. Okay, that means you are taking output at capacitor across capacitor. It is a low pass filter. If you are taking output across resistor, it is a high pass filter. Okay, so so two forms we have seen. In the next case, what we will do is, instead of s square, let us say you have only s. Okay, so s upon s plus 2 into s plus 5. Okay, so in that case, if the transfer function is of, okay, so this is the case. If the transfer function is s, it is a band pass filter. Okay, if the numerator is 1, it is low pass filter. If the numerator is s square, where the number of zeros are equal to poles and all zeros are at origin, then that is a high pass filter. Okay. But third case, if you take this case, that is s into s plus 2 into s plus 5, if you see the numerator degree, it is 1, denominator degree, it is 2, but one more 0 is possible. Okay, so that 0 is present at infinity. Okay, we will consider that as infinity. Okay, so that means in this form, if you see, this is the third case. So you have 0 at origin and 0 at origin and 0 at infinity. Okay, one 0 is present at origin, okay, and one 0 is present at infinity. Okay, so in such case, which is a band pass filter, so which is a band pass filters, in that method we have to follow this method. Okay, what is that is, let us see this. Okay, so if a so just I have written, so whatever I explained, I have written it once again. You can see if p of s is p of general transfer function, p of s upon q of s, if p of s is 1, that is indicates, if p of s is 1, it indicates all transmission zeros are at infinity. Okay, and similarly, if p of s is s, okay, p of s is s, there is a transmission zero at origin. Okay, there is a zero at origin. Okay, so that is the meaning. Okay, so if the zero of transfer function are both at origin and at infinity. Okay, the zero of the transfer function are both at origin and at infinity, use KR form 1 and KR form 2 alternative. Okay, so these zeros are at infinite are removed first. Okay, and then zeros at the origin. Okay, what is the meaning is, so if you see KR form 1, we have done this thing. If you see the KR form 2, okay, we have done s square. Okay, just today in this class. Okay, the zeros are s square. K form 1, it is 1. Okay, so one more possibility is the combination of both. Okay, so I can have transfer function s upon s plus 2 into s plus 5. Okay, so 1 0 is missing in the numerator, so s into 1 I can write it. Okay, so in that case, so you have 0 at origin and 0 at infinity. So in such case, you have to expand by converting into care form 1 and care form 2 alternative. That is the meaning. That means zeros. So care form 1 is applicable when the zeros are at infinity. We have seen 1 because it is 1. Care form 2 is applicable when the zeros are at origin. All the zeros are at origin. This we have seen in today's class. So, but you have both combination, then you have to use in combination, right? So both care form 1 and care form 2 you have to use in combination, right? So this is this case. So here the missing 0, because the numerator degree is 1, denominator degree is 2, so there is 1 0 possible, so that you can write s into 1. Okay, so now this transfer function is in both forms, right? So it has 0 at origin and 0 at infinity. So in such case, if the zeros of the transfer function are both at origin and at infinity, then use care form 1 and form 2 alternative, right? So this that means first we are using care form 1 means we are removing zeros at infinity, and if we are using care form 2 means we are removing zeros at origin, which we have seen in today's class. Okay, so here also our q of s will not change. Okay, s plus 1 into s plus 3, it will be as it is. Okay, q of s will be same, s plus 1 into s plus 3. So you can write s upon s plus 2 into s plus 5. So this thing, right? So your driving point function here also it will be same. But what is the difference is, here now we are writing alternatively. Okay, first thing is, as we have s, we are writing QR form 1 and QR form 2. Okay, so 1 is, if you remember QR form 1, you will have s. Okay, and in the care form 2, you will have 1 by s. Okay, so you are writing alternatively. So KR form 1 and KR form 2 by continuous fraction. So you get band pass filter, right? So KR form 1 and KR form 2. So this is, if you have S, it is KR form 1. If you have 1 by S, you have KR form 2. So now you can write, so it is impedance function starting with 1. Okay, so it is again capacitor 1 by is 1 by 3. So it is a resistor 3.1, because this is admittance. You have to write resistance, so 7 by 3, and here it is again a capacitor 8 by 147. Here again it is a constant, so it is 63 by 8. Okay, so you have to expand alternative. So here in this case, how are we getting constants? In this case, this one. Okay, so in this case, we are getting constant. So how to get the constants in this case, right? So the constants here, you cannot substitute s equal to 0 or s equal to infinity, because in both the cases transfer function will become 0. If you substitute s equal to 0 or s equal to infinity to get the constant, it will not you will not get k value, because it is a band pass filter. So if it is a band pass filter, so it will have non-zero value. You can see band pass filter is this. It will have non-zero value, or it will allow frequencies in certain range. Okay, so at s equal to 0 or at s equal to infinity, it is 0. Okay, so band pass filter you will have 0. That's why you have only at certain frequency range. So how to get the constant in that case is, you have transfer function this as it is, and get the transfer function of this, because you know all the values v2 upon v1, you can get it and compare, then you will get the k. Okay, so in here you cannot substitute s equal to 0 or s equal to infinity. So if you remember, in low pass filter we have substituted s equal to 0, which is this thing 1 by q of s in the previous class. And today in case of s square, which is a high pass filter, we have substituted s equal to infinity. But if you have s, which is a band pass filter, you cannot substitute s equal to 0 or s equal to infinity, right? Because you will get 0. You will get 0 because band pass filter value is this thing. So the only way I think is just find the transfer function for this. Okay, v2 by v1. Now just z1 z2. How to find the transfer function? You can do it, right. So take these two are in series parallel combination. You can do it. Okay, and you will get it, right. And compare with this k, then you will get the then you will get the k value for this band pass filter. Okay, so till now we have seen three forms. Okay, so if the transfer form, so before going to LC ladder, so just to let me quickly summarize what are the two put function form we have seen. One is numerator is 1. One more thing is numerator is s square. Numerator is 1, it is a low pass filter. When numerator is s square, it is a high pass filter, and you have to use KR form 2. Okay, high pass network KR form 2 you have to use. Okay, and it is a high pass filter. Okay, and the third one is, right. So when you in the numerator you have only s. Okay, 1 0 is missing. Okay, because denominator decreases s square and numerator is s. If the missing 0 is 1. Okay, so here you have combination of both KR form 1 and 2. So you have to expand alternative. Okay, KR form 1 and KR form 2, you get band pass filter. Okay, you will get the band pass filter. But if you see, in all the cases driving point function is same. Okay, driving point function is same, but we are expanding according to the numerator term. Okay, if it is 1, KR form 1. If it is s square, or all the zeros, not only s square. If the denominator you have s cube, and all the zeros in the numerator also should be s cube, or at origin it is K form 2, and if any missing zeros are there, that means that zeros are at infinity, then that has to be expanded alternatively in K form 1 and 2. Okay, so that is a thing. So here you can see you are getting the and how we are determining constant in this here, just by comparing the transfer function. Okay, so in three forms we have seen. Fourth form is also possible, like because it is a RC ladder. It is a RC ladder, so you have only negative real poles. Negative real poles you have. So in the numerator, other than constants and zeros at origin, then zeros at negative real axis, zeros on negative real axis, like you have s minus 3. Okay, sorry, s plus 3, s plus 5 on the in the numerator is also possible. Okay, so that how to realize in that case. Okay, if the transfer function is having negative real zeros. Okay, other than this other than these three forms, how to realize that I will discuss in the next class. Okay, so there is some slight confusion in that. Okay, so here just three forms to remember. Okay, if you have constant in the numerator. Okay, because in RC ladder we have only negative real poles. Okay, we cannot talk about imaginary poles. Only negative real poles. Negative poles or zeros are negative real values. So in the denominator you have negative real poles. Numerator, what are possible? Constant is possible. Pole at origin is possible. All constant is possible. Zeros at origin is possible. And s square, all zeros at origin is possible. And real poles. Okay, real zeros. Sorry, real zeros are possible. So real zeros here. If you have s minus s plus 5 or s plus 7 or some real zeros, if you have, how to realize that I will discuss in the next class. Okay. So these three forms you can see, right? Now, so let us see LC ladders. Okay, LC ladders. So the LC ladders is also mostly it is similar to the RC, right? But the difference you should remember, right? You should recall, right? So how will be the poles and zeros of LC ladder? If you remember, LC ladder in driving point function, we are synthesizing driving point function for LC ladder. What will be the poles of LC ladder? Like the poles and zeros of LC ladder will be on imaginary axis. Okay, LC ladder. The poles and zeros will be on imaginary axis, and there will not be any pole at zero. You remember? Okay. So the poles of the transfer function of such a ladder are simple and restricted to the j omega axis, excluding the origin and infinity. Right? Excluding the origin and infinity, right? So the transmission zeros are all on the j omega axis. That is, he's talking, first point is about poles and second point is about zeros. Both poles and zeros will be on the j omega axis, whereas there will not be pole at origin. LC ladder, this we have seen. Okay. So imaginary, when you have imaginary poles, then you can realize using LC ladder, right? So same thing, our two-port transfer function, which is V2 upon V1 or V2 of this upon V1 of this, will be this form. Okay. So divide by Q of S we are doing. Okay. So here, so if you see RC ladder also, we have selected. We have conditions for capital Q of S. How to select capital Q of S? We have conditions. Okay. So here also we will have some conditions for capital Q of S. Okay, what are those conditions? Capital Q of S is selected such that its zeros are on the j omega axis and interlacing with those of Q of S. Okay, so Q of S, if you are selecting, so it will be purely imaginary zeros. Okay, Q of S zeros will be purely imaginary, and it will be interlacing with the poles of Q of S. Okay. Interlacing with the zeros of small q of s or the poles of t of s. Okay, so that is the first point, and q of s can have a zero at origin. Q of s can have a zero at origin, This also we have seen for RC ladder also we have seen there is capital Q of S can have 0 at origin. Okay, and the degree of high. So if you see the degree there, degree of capital Q of S was greater than. Okay, greater than, right? It was not less than. But here there is a difference. The degree of highest power of S in Q of S, okay, can be one more equal to or one less than that of Q of S. Okay. So if transfer function small Q of S is given, okay, T of S is given, that is small Q of S is given, capital of capital Q of S degree should be equal to small q of s, or it should be greater than 1, only one more than small q of s, or 1 less than small q of s. Okay, that is these are the three conditions for q of capital Q of s. With these three conditions, you can select q of capital Q of s. Okay, capital Q of s, right? So that is the first step. You are selecting capital Q of s, and after that you are having driving point function, and you are converting into care form 1, care form 2, right? Based on that. So here, first thing is just like in RC, we will take numerator is 1. Okay. First we will select capital Q of s, and our transfer function form is this form. Okay, T of s form is 1 by Q of s. Right, so RC low pass filter form, right? So here we will take here, and you will divide by capital Q of S, and Z11 you will get small q of S upon capital Q of S. Z12 is this small q of S upon capital Q of S. But here you are obtaining Z12, okay, by constant k. We are replacing by k, as I told. Okay, so this form, if it is a low pass filter form, just like in RC, we have to convert driving point function into KR form 1. Okay. So if you remember LC ladder KR form 1 is this thing. Okay. LC ladder KR form 1 is capacitors will be in parallel. Okay. Right. So let us see one example for LC ladder. Okay. So transfer function is given to this, transfer function is given to this. You have to realize the network. Okay. So you have to draw the network. So you can see first, is it a RC function? No, it is not an RC function because there are no negative real ports. It is a LC function. Yes, it is a LC function because the poles are imaginary. Poles are imaginary, which is a LC network. Okay, and it is in which form? 1 by P of S form. Okay, right. So you can have to convert it to KR form 1. So, and next thing is selection of capital Q of S. So how we are selecting capital Q of S? The poles should be interlacing, right? The zeros of Q of S should be interlacing with this, right? So, and it can have pole at zeros of Q of S can be at origin. So that's why S into S square plus 2. Okay, S into S square plus 2. This is this is interlacing the poles of T of S. Okay. So then that is your capital Q of S. Okay. You have taken this form, right? So what is the next step? This is your driving point impedance function, which is small q of S upon capital Q of S. Okay, this thing. So next thing is to realize into K form 1. Okay, because it is in this 1 by form, you have to realize into K form 1. If you remember K form 1 is, you will have S, not 1 by S. You will have all S. Okay. All S, right? So if you remember that, you will get it right. S is inductor because it is impedance starting with S. You will get inductor, and you have 1 by, this is your capacitor. Okay. 1 by 2. Again you have inductor and capacitor, right? Because it is LC. Okay. So like that you will get you will realize the network. But what is the next thing? Next thing is to find constant. How to find the constant? Transfer impedance or constant. We are finding by, right? So T of S is K upon this thing. So it is here you can use S limit S tends to 0, because if you use limit S tends to 0, 1 by s tends to infinity, capacitors will open. Okay, capacitors will open. There is a full transmission, right? And limit s tends to 0, you will get k by 3. Transfer function is k by 3, and so this is like low pass filter. This is like low pass filter. So and see, in LC network we don't call any low pass, right? So RC we will call, right? So that's why I'm not calling. So you can substitute SC, S tends to 0. Okay, so K is equal to 3. You will get. So figure 1, this figure realizes the transfer function T of S with K equal to, right? So that is how you synthesize this transfer function, okay? Because it is in 1 by 4. So this is same as the first case in RC network. Okay. So just a minute. Give me 1 minute. Right. So here you can see. Right. So figure 1 realizes the transfer function T of S with K equal to 3. Okay. So this is our first transfer function form, right? 1 by Q of S. Okay. There is that this 1 by Q of S. Okay. Now let us see second form. What we have seen in RC network, second form was S square. Okay. All the zeros of T of S are at origin. Okay. So before that we have seen in RC network, if we change capital Q of S, okay, what is happening? Okay. So if you change, so here we took capital Q of S is S into S square plus 2, and the degree of capital Q of S can be 1 greater than the degree of small q of S. So let us take this transform. Okay. So these zeros of q of S, which is also interlacing, right? 1 and 3 is your small q of S. So this capital Q of S you can take 1 to 4 interlacing. Then in that same K I found 1. Okay. Because it is the same problem, one by kind of problem only. Just we are changing capital Q of S. Then you are getting this form. Okay. K form 1 S only. Everywhere it is S. Okay. So you will get starting with capacitor. Okay. Starting with capacitor. So 1 by capacitor. And then you have inductor. Right. And again capacitor. In that form you will get this. But what is the difference? If you see, if you change capital Q of S, but for the same transfer function, if you change capital Q of S, S into S square plus 2 into S square plus 4, and here it is S into S square plus 2 for the same transfer function. If capital Q of S is changing, then total element values are changing. So in the previous case, it was element values were 1, 1 by 2, 4, 1 by 6. And here you have changed capital Q of S. So here it is 1, 1 by 2, 4 by 3, the different values. So if Q of S is changing, design of network is changing. Okay. See, designing is, if you design a network, it is based on some criteria. It will be based on a number of criteria, right? So that's why here particular this is the thing you have to take is not given. Okay. So when you design a network, many criteria will be there. You have to reduce the power loss of the network, and you have to see whether the components are available. You have to see whether the design network is economical. And there's many things will be there. Okay. So same transfer function can be realized with changing capital Q of S. Okay. changing capital Q of S, both are correct, but which one is available to us? Which one is economical? Okay, so bulky inductors are not available, whereas capacitors are available. Just a minute.
Okay. I think you are getting my voice, right? I hope you are getting my voice. Okay. So I was this thing, right? So here, if you change Q of S, the design of network is changing. If you change Q of S, design of network is changing. Just a minute. So let me share the file. Okay. If you change the Q of S, design of network is changing. So that's what I was telling. So Q capital Q of S. So the design will have many constraints. Okay. So that's why if you change the Q of S, design values will change. Okay. Design constraints are dependent on applications. Okay. On what is the requirement and which application it is. Okay. What purpose it is used for. Okay. So it depends on that. Okay. So that's why there is not a this is that's why we don't have a particular method, right? No, not particular method, right? The same design circuit is possible for given transfer function. That is not possible, right? So right. So that is a thing. Here Z11. Okay. So care form 2, care form 1, we have seen, and we are in care form 1. Okay, care form 1, but we have changed capital Q of S, right? So that was our discussion. Okay, so let us see next transfer function where all the zeros are transfer function, all the zeros are at origin. Okay, just like RC. Okay, like in RC ladder, if all the transmission zeros are at origin, which I discussed today, then synthesis proceeds by expanding in KR2 form. Okay, so just you have all zeros at origin, but you choose Q of S, which is interlacing, and driving point function will be same, but you will change it to, you will convert into KR form 2. KR form 2, how is that form? It is 1 by S form. If it is 1 by S form, you can see it is 1 by S form. Okay, convert it, and then you will get it. So 2 by 3, okay, 4 by 5, 5 by 4, okay, 1 by S, and you can see it is 25 by 2 by 25. Okay, 5. So from this, okay. So you got this right. So same. Our next thing is how to find the constant. Same constant you can find. So it is s tends to infinity. You can apply here. You will get x. If s tends to infinity, if you apply 1 by, then the inductors will be open because xl is s into l. S tends to infinity. Inductor will be open, and you have full transmission, right? And k value you are getting from transfer function 1. So you will get transfer function where you are getting k, and here transfer function is 1. So if you just equate, you will get k equal to 1. Okay. So same thing. So if the transmission, so this is what is just like similar to high pass filter in RC network. Okay. And next case, what is one more case possible? We can have some zeros at infinity. Okay, because the denominator degree is s power 4, but the transfer function given is s cube only. It is s cube only, but there is 1 0 that is possible at infinity. Okay, so in that case, just like same care form 1, care form 2 alternatively use. Okay, you can use care form 1, care form 2 alternatively, right? That is s. Care form 1 s will be there. Care form 2 1 by s. Okay, and care form 1 s. So again you have s 1 by s 1 by s. So it is alternatively. Okay, if you do the division, you will get it. So then in that case, you will have LC network this. Okay, so this, right, because S is inductor 1 on capacitor 1 by 2, right? Again it's a in it's a 1 by 1 by S, right? So it's a capacitor again, again inductor, right? That way. Okay, this is about this is so here also we have seen. So here also for LC ladder, in the numerator, you what are possible in the numerator, zero, that is transfer function zeros are can be imaginary, not real. Okay, can be imaginary. Okay, so if it is imaginary, so what is the discussion? If the transfer function zeros are imaginary, because it is LC ladder, only imaginary zeros and poles. So how to realize that network, I will discuss tomorrow. Okay, so that is slightly complicated. Okay, so for RC also, if you have negative real poles, so for RC also, if you have negative real zeros of T of S, and for LC also, if you have imaginary zeros of T of S, then the realization of that networks is little bit complex. Okay, so that I will discuss. Okay, that I will discuss tomorrow, or I'm thinking we can skip that also, right? So based on that, because in two-port function we have studied enough. We had much discussion. Okay, we know how to get that method, how to realize a network, right? Because we have studied in two-port functions, we have studied RC, LC, right? And we have studied low pass, high pass, and realization of band pass. So that real poles one, okay, whichever is missing in the numerator, that I will see. Okay. Mm. And in this module, and after two-port function, there is only one topic, that is minimum phase network, and that is it's a very small topic, so it will not it will hardly take one class, not even one class. Minimum phase network. Okay, so this minimum phase networks you will be studying in your control system as well. Okay, so within next class we will be finishing our fourth module. Okay, so right, so that's all for today's class. Okay, so let me take your attendance. Yeah, actually in between there was some disconnect. So I got an important call, that's why I'm disconnected. Okay, so please don't mind. Thank you. I'm ending the meeting. Right.
Thank you.